So it's my pleasure today to introduce our speaker, Professor Liu Zi-Kui from the Pennsylvania State University. I'm trying to figure out exactly the first time I met him, but it was a long time ago. So he's particularly well known for his work in alloy thermodynamics, alloy phase diagrams, CalFad, and in more recent years he spent a lot of time on integrating these sort of thermodynamic approaches with density functional theory and statistical mechanics ideas, and been very successful in doing so. He did his bachelor's degree in Central South University in China, master's degree of University of Science and Technology, Beijing, PhD from the Royal Institute of Technology, KTH in Sweden. And he's been at Penn State for most of his career. I skipped a few steps along the way. He's a fellow of TMS, ASM. He was president of the ASM International and is the winner of many different awards. As I mentioned before, fellow of TMS, ASM, and TMS's William Hugh Marathuri Award, J. Willard Gibbs Phase Equilibrium Award, real good classics, material science kinds of names associated with all those awards. And so he's the descendant of a long history of very important contributions in the thermodynamics of materials. And today he's going to tell us about some of the work he's been doing lately on quantitative predictions based on the combinations of these thermodynamics, statistical mechanics, and first principles approaches. So please join me in welcoming Professor Zi-Kui to HKU and to Hong Kong, and we look forward to hearing from you. Please.
Thank you. Okay, it's good. All right. Thank you very much, Dave. And a great pleasure to be here, and looking forward to have our joint project, or your project, to work together for that fantastic idea. As Dave mentioned, my name is Zi-Kui Liu. I come from Penn State. I've been there now for 25 years. It's a place I stayed the longest in my whole life. I still enjoy it. That's good. So, today I'm talking about some theories we developed in the last several years. We first started in 2008. We did some calculation. We found it fantastic, but we have not been understand it very well. So since 2008, we believe now we really understand. But maybe next year I will say, okay, I understand some new things over there. But the important thing is that we cannot really predict some very interesting properties without knowing it. So I call it predict unknowns. Okay. But the question is that what do we really know in science today? It's, I think the ones we know for sure is a Ghana state. I think it's the only thing we really know for sure. That means every system has a Ghana state. The question is how do you find that Ghana state? Okay? But we believe we have a way to do that. So I'm going to show you some movie first. I don't know how many of you have seen this one. This is a cupboard on two sides. One side is a cage. Okay, I saw this one last time when I was in New York. After the pandemic, going to see my son in the hotel, had this play in the elevator. Let's see what it is. I have a sound here too. The sound is on. So you see, another side is a bird, right? Two sides. Now, if you spin fast enough, you see a bird in the cage, right? So the question is that, which one's correct? Is the bird, is the cage, bird, or bird in the cage? So which one's correct? Is observation. Of course, you know that. I showed already, right? You say the bird and the cage separated are correct. The bird in the cage is not correct. But you saw it, right? But suppose you did not see it before. You only see the bird in the cage. What would you say? You would say, bird in the cage. That makes sense, right? Okay. So now I'll give you another example. Okay, I talk about some electric material, right? So we know that what some electric material is that if I have a hard part, if I have a hard part here, right? The high temperature, they have low temperature. You know, if you put a temperature gradient, you will see the current flow. And then you were thinking that the electrons are driven by temperature. That's right. So we say we can generate electric current because of temperature gradient. So temperature drives electron. That's observation, right? That's observation many years ago when people found this one. However, is that really true? Are the electrons driven by temperature? Okay. Then turns out you can do experiment. Experiment is that if you cut off this load, you still have a heat flow, right? But there's no current flow. So you could have a temperature gradient, a heat flow, but no current flow. So does that mean temperature does not drive electrons? Okay. So you can do that. So now you get two kind of answer. One is that electrons drive the electrons, get the electric current, and then if you cut it off, you say, no, it doesn't happen anymore. Now the current the electrons are not migrating anymore, even if you have temperature gradient and heat conduction. So that's the second question. The third question I have is that ferroelectric material. Again, this is lead tannate, classical one. At a low temperature, you see that you have Ca ratio, so it's tetragonal polarized. Okay, so you get the structure, you get the center atom, the titanium atom in the middle is going to move, right? Get displaced. Then you say, okay, if you increase temperature, you continue to the X-ray, you finally get a cubic. Then you find the cubic and the titanium in the middle. The question asked you is titanium always at the middle in the cubic structure you got? Or that's just a bird in the cage? So that's the question which bothered me for a long time. So I hope it gives you some answer to you that today to show that this is phenomenon just the bird in the cage phenomenon. There's no cubic. Cubic does not exist in the atomic scale. Just like a bird was never in the cage, but you saw a bird in the cage. So why do you see the bird in the cage? It's because your reaction of your eye is much slower than the spin. Spin is much faster. Okay? So if you spin very slowly, you see bird, cage, bird, cage. But if you spin fast, you see bird in the cage. So both observations are correct. It's just the resolution issue you have. Okay, so we do the letter. So they ask my student, postdoc, to do experiment, right? We do the AMD simulation. Above that transition, you have a cubic, so you fix the cubic lattice. Then you do the vibration. Then you follow the atoms in the middle. You see that, right? The blue atoms are the titanium. So titanium never stays in the middle. It goes, the polarization goes another polarization, it goes all the directions. But it does go through the middle. So it stays at the 0 time in the middle. But it goes through the middle. Okay. So if you think about it, if you can see that atom motion, then you will see the atoms never at the cubic state, right? Just at the 0 second in the middle. So it always travels away from that middle because that middle energy is high. Just like atom diffuse. Atom diffuse from one side to another side, but it goes through this barrier, right? At the top of the barrier, that's where the cubic structure you have. Okay, so what are behind? Why are this happening? What are behind of this kind of phenomenon we observe? It's entropy, of course, right? Because you know that if you have learned the second law, you know that everything is driven by entropy. But the question, how do you calculate the entropy? Okay? How do you calculate the entropy change of anything happening in the system or anywhere, right? Anywhere. So you have to understand this internal entropy production. It has to be positive. That's the second law. But the way is how can you calculate them? How can you quantify it? As you know, that the entropy was first defined by Clausius in I think it's 1940 or 50. I forgot the exact date, but during when he was alive. So he said for an equilibrium system, the entropy change is equal to dq divided by T. And then another scientist say, he doesn't like the differential. He wants to get the absolute number. He said entropy is K times log of W. But it's not from him. That was Planck actually wrote that equation, but he used the Boltzmann constant. So I visited this graveyard. I think if you go to Austria, I encourage you to go. It's a beautiful place. It's a beautiful place. But actually, Boltzmann was not buried there, right? The government moved him there just to show how Austrian people are great people. Okay. And then the first law, second law were derived in Europe. And as you know, the US people science started much, much later. And there's one scientist, Gibbs, he decided to go to Europe to learn thermodynamics. Okay? Then he found that in Europe, the first law and second law are separate. Because first law is equal sign, second law was inequality. You know, equal and equality cannot put together, right? So then Gibbs was smart. So he went there. He said he could put them together. He derived a new equation that combined the law. But however, when he derived this equation, he was very smart. He said, I'm going to remove the second law. So in his equation, second law, entropy of production is 0. That's why he only interested in equilibrium. Okay? So after he derived this equation, he thought he has not solved all the problems here because entropy, you have to be able to calculate entropy, right? So then he derived the statistical mechanics. Again, Gibbs invented the statistical mechanics. So what he did is that he said if you do different configuration, okay, you get the partition function, you get the probability, you get the entropy of the system. Okay? So that means if the system experiences different configurations, each configuration has a probability, then the entropy of the configuration among the configurations gives you that function. Okay? That's 1903 he published the paper. And however, if you make this comparison with the Boltzmann equation, you say if all probabilities are the same, then it goes back to the Boltzmann equation. Right? So it's still consistent. That's very nice. So we have been using this one for since 1901. And when the quantum mechanics was invented, so then people say, okay, because this equation can maybe also apply to the quantum system, and Landau got the quantum statistical mechanics. And when it goes to the classical limit, it reproduces the equation. Okay, so basically, for the quantum, you can also do similar thing, but you get all the configurations sorted out. Okay. But however, when you experiment, let's go back to the cage, right? So they put it in the cage. Okay. The important thing is that you don't really measure configurations. In experiment, you just measure heat capacity. You measure heat capacity from 0 Kelvin to integration, you get this experimental entropy. That's very simple. I was so nice to hear from Cherry said that she measures heat capacity. Okay, heat capacity integration from 0 Kelvin. You take the third law. Third law is kind of postulation, but you can do experiments. You can trap to very, very low temperature. You find the entropy goes to 0. Okay. So that means do integration. Simple. But the question is that you have Gibbs entropy here, right? As we just showed before. Then you have the experimental entropy like this. The question is that are they equal? Or should they be equal? Or can they be equal? Okay. But we do know that, okay, if I have only one configuration, S Gibbs must be equal to 0, right? Log 1 equal to 0. That means Gibbs equation actually describes a pure quantum state. That means each configuration is just a pure quantum state. Pure quantum state is only one configuration, log 1 equal to 0. So that exactly matches what Landau had in 1930s about the quantum statistical mechanics. Okay? But however, the challenge is that we may not get a pure quantum state, right? Okay? So as we go back to this 150 years history of the thermodynamics, Gibbs did I showed the classical thermodynamics in 1973. That's exactly 150 years ago. And then another 30 years later, he derived the classical statistical mechanics. But he did not know quantum mechanics, of course, because it did not exist. But 20 years later, you got quantum mechanics. But the quantum has not been useful until 1960s. Get a density functional theory. And between that, you got a statistical quantum mechanics. Okay, I had another interesting observation because I went to Austria, is that Schrödinger is from Austria. Okay, Kahn is from Austria. Boltzmann is from Austria. Many people use WASP, right? Who did the irreversible program? From Austria. So everything we have today for the quantum mechanics is all from Austria. So that's why you guys should go to visit Austria if you've not been there. Okay. So I visited Austria last time. I was there. The professor let me stay in the Bosman Hotel. So it's all entropy there. All right. So, but because Gibbs only worried about the equilibrium, so he didn't have second law in there, right? But we know second law is so important. Of course, other people are going to study it. Okay. So of course, there are many studies like the semi-electric discovery was actually talked about in second law. But it's really the fundamental work foundation was laid by Onsager in 1930s and Prigogine in 1950s, 70s. But I want to put the caveat, some modeling on the table here. The caveat is actually modeling of non-equilibrium thermodynamics. I call it digitization of thermodynamics. And I also, Dave mentioned that I was in Sweden. Mats Hiller taught me thermodynamics. Third time. I started twice in China, third time in Sweden. And what is different from other thermodynamics we learned before is the internal processes. Mats Hiller put internal process in the thermodynamics. That's what Gibbs removed. Okay, that's a huge importance to me. That's why I can do everything we do today. Thermodynamics is actually that internal processes. But it's important that everything you do, everything you observe, everything you measure are representation of internal processes. Okay. All right. So as mentioned, that DFT is the only thing we do prediction, and so that's 1965, 1963, 64, and developed this exchange correlation functionals, and then did density function theory. The main thing, if you look at this theory, is that any system has a ground state. That ground state has a unique electron density. The question is how do you find that density? And of course, a lot of theories after that. Okay? But in principle, you can calculate the ground state configuration. If you find the ground state configuration, you can calculate the electron distribution. You get an electron entropy. And you can calculate the phonons vibration. You get the vibration contributions. Okay? So that's what we can get from DFT. That's a classical one. So many people do that. Not many people. Some people do that. Many people do 0 Kelvin. Some people do the phonons. But it's another very important thing not so many people do is the non-ground state configuration. Okay? The reason is because just like the bird on the cage, right? On the cage. So what happens, they have different configurations. At high temperature, try to mix them together. If you mix it fast enough, you don't see bird, cage, you see bird in the cage. Okay? So that means if you want to describe the process, you must have both bird and cage, right? You cannot just have one of them. Okay? The idea is that you have to have as many configurations as possible, including the ground state configuration. But you all know that for the non-ground state configuration, it's symmetry breaking, right? You break the symmetry. But each of them have a unique electron density. You can do the entropy calculation for all of them. That means for each configuration, you get a free energy. Okay? Now, that becomes the beauty now, right? Suppose you have the bird on the cage. They have the birds have the free energy. You start to mix them together, you see bird in the cage. Okay. So that means we get a total entropy. Okay. So now that means we have to add the quantum entropy into our formula. That means experiment entropy would have two components if we're going to predict them. That we have the quantum entropy and the Gibbs entropy together. Okay. So that means we have to change our statistical mechanics now, right? That means entropy now have two components, not just one in the Gibbs statistical mechanics. If I have two components, our homogeneous energy has to change too. So instead of EK, we have to change the FK here, plus this configuration entropy. If you change out further, you find the partition function has to be changed. Instead of EK, you have to use FK. So that makes a huge difference because your probability is very different than before. Okay. Of course, if with pure quantum state configuration, then SQM equal to 0, right? So it reduces the one you have in the classical one. Okay, so what it means that's Gibbs statistical mechanics. And then I give the talk about our presentation, our approach. During the pandemic, the bad thing is that you don't see people. The good thing is that you get more people to your meeting, to your presentation. So I give a talk in 2021 at Duke University. which I did online. So as part of our method, I said that we don't have any name for our approach. Whereas this is multi-scale, right? From quantum scale all the way to classical scale is a multi-scale entropy. It's one at the end of the discussion. That's one postdoc from Buffalo. So Dr. Liu, you should call it Zentropy. So now I find Zentropy statistical mechanics. Okay, so this is 2 years old now. So the idea is that it changes the entropy with this statistical one. Okay, then you do the add the quantum one. Okay, then you change EK to FK. Then you change EK to FK for everything. So everything is exactly the same. But these two are also the same. If all SK equal to 0. That's the pure quantum state. That's what Landau's quantum statistical mechanics is about. So that was the pure quantum state. That's basically the story. Okay, now when we did that one in 2008, we want to solve a problem with cerium. Okay, what kind of cerium at that time? We want to predict the PT diagram of a cerium, phase diagram. Okay, so to summarize it, basically that this is the standard statistical mechanics. You have configurations. You do the entropy of the system, which is the pk log of pk summation times kp. Each is very important in Gibson's work is that each configuration must have the same MVT as the system. Okay, you cannot take a part of it. You have to take the whole system. Okay. But however, if each configuration has its own entropy, you have to add it, right? So that basically that means in addition to the configuration entropy among configurations, you have to have the entropy of each configuration together. If you do that one, you can go all the way down to the quantum mechanics. So that's the only place we know. So we start where we know. We do the internal degree of freedom. We put them back together, predict we do not know. That means if our theory is correct, we should be able to predict something we do not know, right? So that's what we call Zentropy. So basically put the top down and the bottom up together so we can predict accurately the entropy of the system. If we can predict the entropy of the system, we supposedly can predict everything of the system. Okay, so we did example, cerium. Cerium was the only element on the periodic table which is non-magnetic at 0 Kelvin and become magnetic at high temperature. So you can do 0 Kelvin calculation. You can see that. You can see that the red line is non-magnetic. Okay, the EV curve has the lowest energy. At the high temperature, it becomes ferromagnetic. There's a blue dot here. But of course, when you have the ferro and the non-magnetic, when the ferro starts to spin, you got the anti-ferromagnetic between. So the half field symbol here is the anti-ferromagnetic configuration. Only 3 configurations. We can calculate the free energy because they're all stable. Then we can put them together to calculate the total free energy of the system. At 0 Kelvin, it's a very sharp change. But temperature goes up because that pk log pk term, then this starts to drop until to some point, the two sides become one side. So that's where the critical point is, because the second derivative and third derivative become all 0 at the same time. So that means with these 3 configurations only, we can predict the critical point. That's the phase diagram. Okay? So the derivative gives you the pressure, right? So we can predict the temperature pressure phase diagram with the solid line is a prediction. The symbols are from experiments, including the critical point at the top here. So we predicted this one back in 2008, 2009. So what is the importance of this line is that at the critical point, we get the divergence of a property, right? Singularity. Okay, that means we can predict singularity. How do we show that singularity? We can change the pressure to volume. Then you see that the slope between T and the V is horizontal, inversely is infinite. That means the critical point of the volume, some expansion becomes infinite. Okay, that's the singularity. Again, let's all predict from that one. And you can see the phase boundary here, two symbols are phase boundary. You can see the prediction between these only 3 configurations. I can predict it reasonably well, critical point and the phase boundaries. And what you can actually figure out what happens that when the different temperature, you actually see this kind of the shaded area is what is the extra entropy put in. So that's a statistical. The individual line is from quantum mechanics. The shaded area in the middle is what you have as the configuration entropy. What do you see? You can predict the barrier between the 2 configurations. 2 states, not configuration anymore, 2 states. Because each state is a configuration of many, 3 of them with different probability. So what does that mean? That means we typically know that when you have the French goes like this, you got instability, right? You got the French, you cannot define the entropy because it's unstable. However, there's no instability here for the individual configuration. It's always they come together. The frustrate the system has an instability, but the individual atoms, individual bonding, has no instability. Okay? So all the bonding themselves are perfectly stable. Turned out recently the experiment, if you measure locally, it's always stable. It's only when you put them together, it shows instability. Like a bird and a cage, it's the exact same thing. Okay? You have bird and cage is always perfect, but you spin them too fast, you see the bird in the cage. All right, so we did another example, is the iron 3 platinum, that's INVA. Remember here I showed, the previous slide I showed the volume, the sum expansion is positive, right? The slope is positive here, okay? Always goes up, okay? But the INVA alloy is different. INVA alloy is volume going to decrease, right? Decrease, okay? Again, we take the 512 spin configurations, but 37 are unique. We can calculate all of them at 0 Kelvin. Now you see a very interesting observation. You see all the metastable configurations we have on the left side here. It also has smaller volume than the ground state. But in the previous case, metastable has a larger volume, right? Okay. So I want to keep that in mind. That's the origin of negative sum expansion. Has nothing to do with the bonding become soft modes. It doesn't exist. Okay, doesn't exist. The calorific energy. So it's very interesting that if you calculate the energy of the configuration, the ground state is always stable. If you look at the energy, you have no transition. Because the ground state is always stable. You talk energy. However, it's a competition of probability, right? You see the probability at 0 Kelvin, the ground state is 100%. Okay? The non-ground state is 0. But when the temperature goes up, so even though the ground state is still more stable, but the population of the ground state starts to decrease. It can actually even decrease 15% at a high temperature, just because it's 1 against the 512. That's a number game, so you cannot compete. They're going to lose. They can calculate the negative sum expansion at 0 pressure. You can see that the symbols again from different experiments, the lines from prediction, from this 5 to 12 spin configuration completely predicted from the first principles and without any model, without any fitting parameters. And we calculate the phase diagram, TP phase diagram. Again, symbols are from experiments and lines from prediction. No model, no fitting parameters. Now, if we change this pressure to volume, what do we see? So each line curve is for a fixed pressure. This dotted line is with the 0 pressure, ambient pressure. You see the volume sort of increase first, and then the volume decided to not increase anymore, then decided to decrease, and then increase again. Okay. And then, of course, there are a lot of theory to explain them, talk about the bonding change and so forth, right? And turned out there's no soft mode here. Okay. It's actually now a new experiment by the Brookhaven National Lab. They measure local bonding. There's no soft modes. Okay? And the local bonding does not decrease as temperature goes up. Temperature goes up, the local bonding is always increase. So the only reason you have negative sum expansion is because when the temperature goes up, so population of the smaller volume one increase. Each of them have some expansion. But total volume could decrease because the smaller volumes ones replace this bigger volume one. So total volume decrease. So it's no soft modes based on this classical theory. We hope we can convince people on that. Okay. Now we did a lot of examples. We did pure iron, we did pure nickel. We did a very interesting superconductor here. Okay. So I presented to the physics people. They said, no, it cannot be right. You know, this soft modes must be there. Okay. Then they give me a very interesting problem to solve. It's each uniconate. That's called a strong coordinated. That means DFT should not work on that case. It should not work. It's too strong coordinated. So people say you do the U, you do the dynamic mean field, whatever how new method to describe it. Then I said, okay, let me try this one, right? So we can give the configuration. We can calculate all the configurations by DFT. We get the free energy. Okay? So then I say, if I take the Gibson statistical mechanics, use EK, because I have EK, right, calculated, I can predict the probability change when the ground state becomes less than 50%. That means the system is not a ground state anymore, but a mixture states. That cross point is like 81 Kelvin. Okay? And then we say, if we take the free energy one, the new statistical mechanics, the crossover is 144 degrees, and the experiment is 145 degrees. So the question is that how you define that 50% as a transition, right? So if you think about the experiment, if you sample the system, if the majority of your sampling is ground state, you will find it's ground state. But as soon as the ground state becomes less than 50%, when you sample it, you don't see the ground state anymore. Okay? Your sample is not a ground state anymore. That's why you get this transition. That's actually what magnetic property measurement is about. Okay? Because you see the spin, the magnetization, which change now than before. Magnetism goes to 0 because you don't have this well-defined magnetization anymore. Okay, so I hope I convinced the people strong correlated the system is because we don't understand it. It's not because it's strong correlated, it's just because you have not sampled enough of the configurations to put them back together. Okay, so it's really, it was very nice talking with Tongji the other day. So he made me realize that because I don't do MD, right? I want to understand how MD works. So he explained to me. Then I think, oh, now I understand why the MD cannot accurately predict transition temperature. Okay? I hope we can do some work to make that accurate prediction by MD. Okay, the first is that in the MD calculation, when you fit in DFT, you don't fit into all configurations. You fit some configurations. Okay? So you want to fit all of them. That's the first one. Second one is that you cannot only fit into zero energy, you have to fit into the free energy. Okay, that means I think Suboshi told me you did that already. You have the force into the picture, right? The force, because you calculate the phonon from the force. If you have all the forces for all configurations, the last one is the sampling. You have to use the free energy to do the partition function sampling. That means when you talk about probability of each snapshot you have to use the free energy of that snapshot to do the probability calculation. You have all three together. I hope you will demonstrate to me, you can predict it. Okay? Your transition temperature will be less than 5 degrees disagreement with the experiment. Because that's very good, right? Because MD has this fantastic approach, can do a very large system and efficiently. If you use the Zentropy, you cannot do so many of them, right? Because you're limited. Okay? Particularly if you have many configurations. Okay, and I hope really that'd be fantastic. I challenge the Tongji to do one is for titanium PT diagram. Predict the titanium PT diagram with the experimental accuracy of temperature and pressure for all the phase boundaries. Okay, that'd be fantastic. I had a student do that. I had one student do that one. We could not predict it. Because at that time, our Zentropy was not developed yet. You could not do that, okay? And I was talking with a few people. I think we need to find enough configurations. We know how to calculate the free energy quickly, right? So if we put all three together, I really think the universe is predictable. Okay? I had a conversation with the person who developed the long-term, short-term memory for the machine learning. Right? His paper, single paper was cited 70,000 times. Okay? Everybody said that paper, right? He asked me the question. He said, is the universe deterministic or stochastic? He answered the question. And he had 2 papers published in 2015 or 2010. Is the universe is computable. That's his paper. Computable universe. But then he... Sorry?
I think it says Einstein versus Bohr.
That's right. So Einstein said God doesn't play dice with the universe, right? But then my answer to that person is that it's a scale dependent. If you look at the entropy equation there, right? The low scale is statistical. The high scale is deterministical. But in order to get the deterministic outcome, you have to get started with statistical, stochastic. I hope the entropy actually unified together. That's why the entropy has two terms. One is a quantum mechanical term. That's purely the statistical, right? And then you have the probability one, which is larger scale probability. But when put it together, you got the heat capacity measurement. Isn't that amazing? Heat capacity is deterministic. Any material, like you measure in the lab, you get the same heat capacity every time. You never get a different heat capacity if you do the same material, right? That's deterministic. All right. So we did that all right. So I'm very happy on that one we did all. Then I was taking my sabbatical 2014-15. Sabbatical was a very interesting sabbatical. There was one guy that does work about diffusion. Of course, my advisor is a diffusion expert. He had developed a database, Dijkstra, everything. Worked perfectly. Everybody uses it. And then I went to that person in Australia. He said he's working on the thermal diffusion, right? You take the sample, you add the heat reagent atom to the move. Then he told me there are two diffusivity of that atom. One is the first term with chemical potential, another with temperature gradient. I have two terms, yeah? Then I said, I don't understand, because my professor is only one diffusivity each element. That's no two. It's only trace of diffusivity of one element, right? You cannot have two diffusivity. But he said, no. Onsager said there are two. Onsager equation has two. No, has many, not only two. Has whatever number you have. Then I said, I don't understand it. Something must be wrong somewhere. Either my professor is wrong or Onsager is wrong. They're not coherent. Okay? So then I went back to talk about the thermodynamics. I said, can we understand thermodynamics, right? So the first equation, this is not my equation, this is my Marcellus equation. The entropy of change of a system has three terms. One is the heat, another one is the mass, the third one is the internal process. Okay. So you put that back in there, you define the chemical potential, you define this kind of different quantities. But when Gibbs did the trick in 1873, he said, I'm only interested in equilibrium. I dropped the last term. But last term is the second law. So his combined law is not a combined law, okay? It's only for equilibrium, so he dropped the second law. But anyway, that's fine. But if you really want to consider irreversible process, actually any process is irreversible. There's no reversible process. It doesn't exist. Anything we do is irreversible. That means we have to be able to calculate it. The trick is that, in addition, except to put it as an inequality, why don't we just write out the equality? The equality is that any process is going to do something, and that process has driving force. So if we do this one, that's what Massey did. Okay? Massey did it, I put this back. That means this term now is positive, but we can describe it. Okay, so how to describe it? Okay? So that's my invention now. So I said I have to describe this guy because nobody describes it. But I have this one. Okay? Then I said any internal process has four things it does. The first thing is that either get some heat or consume some heat. That's the first one, right? That's the one the Clausius had. And then that process may take some reactants, like a nitrogen, hydrogen. You're going to produce something. Oh, they may not do it, right? But the most important thing, which is very hard to do, is that it reconfigurates itself. Okay? So if I put the four terms together, I can describe it. Okay? So I have four terms, describe. Then I can say, okay, this whole process, which has four things happening, is I can use that one parameter to describe that process. Then that process has driving force. The question is, can we calculate it? Okay? Let's look at what we know for this kind of problem. We know the Darcy's law, we know the Fourier's law, we know the Ohm's law with the Fick's law, right? But if you look at these laws, we have that. There's two of the conjugated variables. Okay? The Darcy law is about the pressure and the volume. So it's conjugate. All right? And the electron and the voltage are conjugate. But the heat and the temperature is not conjugate. What is conjugate of temperature? In Gibbs's equation, it's entropy. So actually, we should not put heat here. We should actually put entropy flow. It's not heat flow, but heat is different from entropy, right? Remember, entropy has three terms: heat and mass and the configuration. That's another misconception. Okay, but the last one is even more misconception. We should forget about fixed first law. It's completely wrong. The reason because the diffusion is not driven by composition. Diffusion is driven by chemical potential. Okay. Okay. So that's what we should write it. Okay. We should write the first law, but the entropy on the left side, not by temperature.
So Uncycled.
It's so much fun. Yeah, okay, so now, but the question is that, so the reason Onsager developed this theory is because before Onsager, this observation that the heater can conduct a current, right? You put a heater there, it generates current. That's cross phenomenon because heat and entropy together, current should be get a voltage together. That's cross phenomenon. So actually, Thomson, Kelvin all get equations here. But Onsager systemized it. And even more important, and he pointed out many things. So the direct phenomenon is between conjugate variable, cross phenomenon is between non-conjugate variables. Okay? Now you can say temperature gradient can generate heat, entropy, which is actually called entropy now. And that's the direct phenomenon. But if temperature cannot drive an electron, diffusion and volume flow, that's all cross phenomena. And then electric field can generate electricity, that's direct phenomenon. Then it can also go to heat conduction, atomic diffusion strain. Okay. Same for the stress. Stress, of course, it will be volume change, flow, but it can also generate electricity, atomic diffusion, heat conduction. So it turns out that we have way more cross phenomena than the direct phenomena. Okay. How do we solve that problem? Onsager did it. But actually it's not fair because Onsager's equation was there before. Thomson had the equation already. But Thomson only have two terms. Okay, temperature and composition, electron current, right? 32 terms. But the Onsager said, no, let's make it all terms. So any flow, it depends on all potentials. That's his idea. Okay. Then he said, he made another very important contribution, so to speak, is that the error matrix is symmetric. That's called Onsager reciprocal relation. That's why he get Nobel Prize. Okay. That's where I get into the problem is that I'm doing chemical diffusion, and my host is doing thermal diffusion. He told me there are two diffusivity, okay? And they're independent. Then I said more than one independent diffusion coefficient for one element. That's simply wrong. There's only one diffusivity for one element. What it means the atom has to go overcome. That's it. Whether how it is driven doesn't matter. It's only the atom from one side to the vacant side. Jump over. That's only one mechanism for diffusion. There's no other mechanism. It's only the driving force or the barrier, how much they are. Okay. So that means I did not believe Onsager equation to start, but I could not prove it. And in the 2014 and 2015. So, I didn't have project. So I buried that problem in my brain. That professor always invites me to go to his meeting, diffusion meeting. So every time I go to present a little bit, present a little bit. Then I use this one argument. It's only one diffusivity for each component. It's the mobility of the atom. Mobility of the atom can connect to the tracer diffusivity with the Einstein equation. However, in the experiment, we measure so many diffusivity, right? Just like the Onsager equation. What it means is that mobility can get a driving force, get an error parameter in the flux equation. Okay. If we change from chemical potential gradient to concentration gradient, we got a matrix now. So how do we get that change? We'll talk about later. And then because the concentration you have the one dependent element, you can remove the dependent element because you still have a matrix, right? That's first the transition. That's called intrinsic diffusivity. The intrinsic diffusivity is actually still the one diffusivity, but you get a matrix now. What does it mean? That means they are not independent. So what is the relation? If you can think about it, if you don't know, I'm going to show you in a minute. Okay? So there's one transition. Another transition my professor made, and his PhD thesis, and John Owen's PhD thesis. Then he said, okay, when you talk about the one diffusivity, what do you mean? Because the atom since is moving, right? Moving, you must have a reference state. So when you talk about the mobility, you are talking about the lattice fixed frame. You are sitting inside the lattice, CR the move. So you are moving with the system. Okay? Let's actually go back to Einstein's relativity, but not in that sense. So, but you say if you're standing outside, you are changing frame of reference, right? Because things is moving now. So you get another mobility error parameter. Now again, it becomes a matrix. Okay? But you still use chemical potential gradient. Now it's not only the chemical potential of the diffusion species, but the chemical potential of all species is the matrix. And you can change this one to composition, right? From the chemical potential to composition, you got the chemical diffusivity matrix. Then you remove the independent one, you got the typical interdiffusion coefficient. So we have mobility, or tracer diffusivity, we have the intrinsic diffusivity, we have the interdiffusion coefficient. And these three sets are the matrix, that one is a single variable. So what's the connection between all this diffusivity? That's my professor did in 1992, actually in 1982 in his PhD thesis. Okay, it's the thermodynamic factor. So all those parameters, we call it kinetic parameters. Even people have this Maxwell matrix. Okay, they are all derived from one diffusivity by times the thermodynamic factor. So all the diffusivity is kinetics plus thermodynamics combined together. But the kinetics is only one parameter. Okay. So that convinced me. That means all those matrix, these people talk about in Onsager thermal diffusion, it's a thermodynamic factor times another kinetic factor. All right. So of course, I'm not the only one to question Onsager, right? And if you go back, there's many questions in the literature. The particularly interesting one to me is this one people told me, Truesdale, and it turned out that he did a lot of work, but he's more like argumentative. Talk about Onsager is wrong, but he really doesn't have fundamental to show Onsager is wrong. But this guy's work is pretty interesting, very pretty recently. They showed that the flux of an element is only proportional to its, they call it a general potential, chemical potential. But it just means this one has to have all the contributions, as it exactly have. But however, the interpretation was wrong, okay, because they still believed the Onsager one. So I wrote a comment to question their argument. But Marcilla wrote his book, say Onsager relation is not fundamental, it's phenomenological. But he didn't say whether, what if you do with it? And in another kinetic book, a very big one, it also says that it's not fundamental. But however, there's no general solutions provided. So what we can show here is when provide a solution, there's time. So there's 4 questions about Onsager theory. The first one, is it symmetric? You can diagonalize it. So what is the result of after you diagonalize it? Okay. What are the driving force after you diagonalize the matrix? We know exactly that already from combined law. Chemical potential driving atom motion. That means you talk about the atomic motion element, it must be only chemical potential left. That's combined law, right? That's the first one. Second one is that he used the microscopic reversibility to derive that symmetrical relation. However, if you talk about microscopic reversibility, you have to apply Gibbs to Hammond relation. If you apply Gibbs to Hammond relation, the potentials are not independent. You have to remove at least one of them from the equation. Which one to remove? It turned out to remove everyone except the only one you keep. Okay. The third one is that if that chemical potential equals 0, for example, you still have a flux of that element. So what drives that element for diffusion if the chemical potential is the same everywhere? The third one is that now you have a flux, but you have no driving force. Time together, you have no entropy production. But how could it be a flow without entropy production? Any flow should have entropy production, right? Okay, so as to the 4th question, of course, my answer is that it's very simple now. There's no cross terms in the combined law. So his cross term is just because his frame of reference changed. Okay? That means all the entropy reduction, we can calculate the entropy reduction of any process. If we define based on Marcellus' book, then we can calculate equal to the delta yj times the flux. Then flux must be only function of its own gradient, the chemical potential, or the conjugated potential. And then you can actually the second law, everything is beautifully fulfilled. All right, so what it means is that, but we still have to explain how the heat drives the diffusion, right? How does the temperature gradient drives electron motion? Or diffusion in general, thermal diffusion. So this is our general equation. Flux of a molar quantity is only proportional to its own conjugated potential gradient with a coefficient. That's a true kinetic coefficient. However, that potential gradient is a function of all variables you can control in the system. So that's where the cross phenomenon come in. Okay, that means you have the first term you have here will be the conjugated variable, right? Second one is non-conjugate variable, molar quantity, and non-conjugate potential. Depends on how you control the system. Okay? So that means the exact what happens is that the first term is the conjugate variable, the next two terms contribute to flux. Okay? That means go back to some electric experiment. You add a temperature gradient, and then you do not allow the current flow. What the system does, system moves the electron to a distribution balance your temperature gradient. Makes the chemical potential of the electron equal to 0 everywhere. There is no current flow. So it's nothing to do with, well, it's not temperature driven, it's chemical potential driven, but the chemical potential is affected by temperature. All right. So basically, we can give an example. The example we shows here is that it's a semi-electric, right? At the initial time, time equals no temperature gradient, no concentration gradient, no chemical potential gradient difference. Now, if you at the T is infinitely small, you add a temperature gradient, and there's no electron migration yet, so the concentration gradient of electron is still 0, but the chemical potential is not there anymore. Okay? Temperature gradient get heat flow. Okay? That means now the electron is going to move because now you get potential. So electron to move. Now this time, because no current flow, so electron move after a while, there will be a concentration gradient of electron in the system. Okay? At that time, the chemical potential is not 0 yet. It's continuing to move until at some stage that the chemical potential electron equal to 0. There's no current flow anymore. Electron stops. Oh, very fast, right? Electron moves very fast. That's where you measure Seebeck coefficient. What does it mean? Seebeck coefficient is a purely thermodynamic function with the chemical potential of the electron to temperature derivative. Okay, so we can calculate one. If we write the flux equation for electron like this, and the chemical potential is function of electron function of concentration and temperature, that goes back to Thomson equation before Onsager's formula. And then you have two terms now. This one, electron gradient will give you the potential voltage, internal voltage, and have a temperature gradient there. And it turned out the Seebeck coefficient is basically partial entropy of electron. Now you can make it 0 with no current. You calculate, you get a Seebeck coefficient. It's a partial entropy of electron. But because the electron goes a different direction of the current, you get a minus sign. So that's why the Seebeck coefficient for electron N-type is minus. But you get a P-type, or you can directly get the parity coefficient of Thomson relation, because electron carries heat. So you get this equation, you don't need to derive it. It just comes out directly. And if you get a P-type, then it's the whole conduction, then the positive Seebeck coefficient. All right, so we calculate something, two systems, lead tyrrhanate and also tin tyrrhanate, selenate. And for the lead tyrrhanate, you can do the P-dope and the N-dope. Then you get two different positive and negative Seebeck coefficient, but this is P-type, you get a positive. We'll calculate lead tyrrhanate. For this one, we can basically calculate electron chemical potential, electron potential, chemical potential of electrons. All right, so go back to this last problem. I get 2 minutes. So we know that this is tetragonal, right? It's cubic. But however, you look at individual atom, it's not cubic. Individual titanium is always tetragonal, but it switches directions. Okay? And if you get low temperature, it switches less often. So just like the bird in the cage. So the bird in the cage is tetragonal, but it's flipping all the time, you see cubic. So cubic doesn't exist. Cubic is the velocity is too low to measure it. Okay? So it turned out it was done experiment already. As a paper here in 1994. People do the X-ray measurements. They showed that even at the cubic temperature above, it's always tetragonal locally. But this is our AMD simulation from that picture I had, the red one, because we take the experiment lattice parameter, simulated the one. You can also polarization too. If you look at the X-ray and the neutron scattering, you get 0 polarization, macroscopic one, but locally you always have it. So we need both, but now the last problem, how can we predict it? Turned out there are only 3 configurations. One of them is ferroelectric, another was 90 domain warp, because when the polarization goes to 90 degrees, another 180 degrees. So basically only 3 configurations. We take the data from literature, we calculate the probability. Turned out the literature has 2 sets of data. Okay? One of them is by Vanderbilt as group. You get 35. The predicted the 50% of the ground state is 77.6 is about 13 degrees higher than the experiment. That's the best prediction in literature ever. I have not seen anyone close to that yet. But if you take another set, is